Welcome to another episode of Value First Expert Interviews, and today we have a distinguished professor of computer science, industrial and systems engineering, the TRW Professor of Software Engineering and founding director of the Center for Systems and Software Engineering at the University of Southern California. He is known for his many contributions in the area of software engineering. Bain's research interests include software development process modeling, software requirements engineering, software architecture, software metrics and cost models, software environments, and knowledge-based software engineering. His contribution to the fields include the constructive cost model, also known as the COCOMO model, the spiral model of the software process, the theory W, the win-win approach to software management and requirements determination, and two advanced software engineering environments, the TRW, Software Productivity System and Quantum Leap Environment. He has written several books, including the Incremental Commitment Spiral Model and Balancing Agility and Discipline, and more, right? I don't need to go through all of them. But I am very honored to have Professor Barry Bain. I say it right?
Yes,
Bain,
right.
yeah. With us tonight, or today? Tonight, yeah.
Good lighting.
Good lighting, so it must be day. So, but before, I'd like to go into all this systems engineering where you're an expert. But before we go there, I'd like to ask you, when you were, can you go back, when you were 10 years old, 15 years old, who were Barry then? What was your interest? Where did you live?
Okay, well, I was born and grew up in Santa Monica, California. As I mentioned in the talk earlier today, I was fascinated by space travel and science fiction and all of these ideas bouncing around what the future was going to be like. And
where did you get the interest of space travel? I mean, as a kid, where did that information come from? Not the internet, right?
Not the internet. It was basically the magazine. It was Astounding Science Fiction and Galaxy and the like. And there were books coming out. Ray Bradbury was I was also a page in the Santa Monica Public Library. People like Ray Bradbury would come into the library and ask for a particular book or magazine, and I would go down into the basement and find them for them. So some of these people were real people for me as well.
So you were working in the library as a boy who were getting information?
Yeah, high school junior and senior, yeah.
Yeah.
So, it was Christopher Isherwood was another person who came in and had questions like that. And so they would actually talk with you for a bit and that sort of thing. So they became sort of role models and
Did you want to be an astronaut?
what?
Did you want to be an astronaut?
I wanted to,
Mm-hmm.
and at the time there was a call for people who might qualify as scientists instruments.
Yeah.
What basically caused me to not apply was that I was generally taking our 4-year-old and 6-year-old daughters to a playground where there was a and,
Yes.
and the girls would go round and round, and I got dizzy doing it. I'm probably not going to be a good astronaut, so I decided not to apply.
Right. They had those tests, didn't they? Where they took the candidates in these machines
Yeah,
and
right.
spun them
Yeah,
and
right.
see what they can handle.
Yeah, right. Yeah.
I myself, I was, as you probably know, was a pilot, learning how to fly planes, and also when I got these little airplanes, it's really bumpy and they
Yeah,
fly around.
right, yeah.
I also tended to get a little dizzy,
Yeah,
feeling a little hot.
Yeah.
So maybe I wouldn't be a good astronaut either.
So I would basically be a virtual astronaut by reading all this stuff.
And that's maybe, is that what brought you to the area of science, of engineering?
Right, yeah. So, and fortunately, my first job was as a summer intern at what was called Convair at the time, was now General Dynamics, and so I showed up as I'm one of your summer interns, and the guy in the personnel department said, "Yeah, what's your major?" And I said, "Mathematics." And he looked up his board and said, "Then there's propulsion, and there's guidance and control. There's the digital computer laboratory. Well, digits are mathematics, so why don't you go there for the summer?" And so basically, I went down, and in my first day on the job, I was escorted into the computer, which was about as big as this room that we're in right now.
Right.
And he said, "Now listen, this is the most important thing I'm going to have to say to you, but we're paying this thing $600 an hour, and we're paying you $2 an hour, and we want you to behave accordingly." So fundamentally, I would do a lot of manual execution and double reviewing everything before I put it on the computer and that sort of thing.
So do you remember what the computer was? The
It
name of it?
It was done by Univac. It was called an ERA 1103.
And what was the technology behind it? Was it?
Well, the memory was basically a vacuum tube.
Yeah.
And it basically had 4,000 cells in it.
4,000 cells. What, in the vacuum? No, in the vacuum tube? Or how did that even work?
Well, the bunch of vacuum tubes that were in there
Right.
was sort of the equivalent of 4,000 instructions. So that was
Right.
the biggest program you could write.
Right.
But it was also the thing that was your best debugging aid, because fundamentally when your program was running on the computer, you were supposed to watch the screen, and if one part of the screen was starting to light up and burn itself out, you felt that we're in a tight loop and we better turn this thing off.
So the vacuum tubes itself were hot, or what?
Yeah, well, the vacuum tubes were the memory, and so your program was part of the memory, and then you would execute these things, and the tube would light up, and so it was.
Now, what was some of the first things that these computers, early computers, were useful for? like, you know, I understand. So you can have some simple, so it's mostly math, formulas that were equations that were put in, but what was the data that went in and what was the data that went out that was saying, wow, this is useful, gives value to some stakeholder, because that's sort of my pitch all the time, talking about how to give value to stakeholders. Now we have, way back, one of the first computers, it can compute something, but how did that give value to a stakeholder in the early days?
Well, in the late 50s, the Defense Department invested in 3 different intercontinental ballistic missiles, and General Dynamics got the contract for one that's called the Atlas, and Boeing got the one for Minuteman, which was a solid rocket, and I think it was Lockheed Martin had another liquid rocket thing. So there was a lot of competition, and since there was a lot of concern about the Russians and the like, there was sort of an infinite budget. So there was a lot of opportunity to build things that were fairly ambitious.
And can you remember one of the first sort of direct values that people got out of? So I see we had these missile systems, we had big budgets, so that's the money coming in. But then I guess you could do what the computer did by manual, right? Like you still can today. You could do the job without the computer. But obviously the computer must have given some people some advantage. What would
a
be
good example is that after I graduated, so I basically did 2 summers, and then after graduating, I got a full-time job there, and one assignment I got was that the people who were trying to get us more manned space flight wanted to put a lot of the space capsules on top of an Atlas missile.
Okay.
They knew that there was a chance that the missile was going to start to blow up and the like, so they said, we want to put an escape rocket on top of the missile, and we need to simulate what would happen if the thing started vibrating or shaking or wobbling around in its ascent, that if you shot the astronaut off, it would not end up getting hit by the booster.
Right.
So writing that simulation was basically one of my jobs, and basically we found some guidance and control approaches that made sure that the astronaut wouldn't eject and then get hit by the booster.
Okay.
So
That's great.
You couldn't do that just by hand.
Right, that'd be too much.
Yeah.
So that was some of the early, because we're still, in my world, we have computers and computer systems, and then I think we need to be better at understanding, well, what value does it provide, and how do we use the technology to give value? In our conference, we're talking about this blockchain technology, for instance.
Yeah,
A lot of people are like, yeah, we need to do blockchain. And it's like, well, for what purpose, what value is it going to give? And that's less clear. But they want to do blockchain. You know, it's like the most popular, one of the popular things to do. So I think it's nice to go back to when the computers were so simple, they couldn't do as much as they can today, not even
Yeah.
close,
Uh,
but still it was giving some value. What is that value, right? So we have an example of that. Now,
So yeah, in
Tell me more,
blockchain,
so-
I've visited Estonia a couple of times. I've been very impressed with what they are doing with blockchain.
yeah,
Basically, all of their citizens, they don't have worries about electronic voting. Basically, there's no way you can cheat, yeah. And you don't need a credit card. You just, where you have a card that basically identifies you and your blockchains, and so you don't need to. A lot of accounting and things like that are done for you, rather than having you write checks for this and write checks for that.
right. So they're getting lots of value from it, that you don't have to do that manual work, and cheating is
Yeah, right.
more difficult. I'm guessing it's still possible, right? Even with the blockchain, there's something underneath that somebody could have a key to.
Yeah,
And, yeah. I'm a little suspicious that there's always some way to cheat, but it's harder.
I would imagine there are some super programmers in their government that if they wanted to, but the Estonians don't seem to be the kind of people who want to cheat, and it could cause a lot of problems. The other problem is that the Chinese are capitalizing on these kind of things, and they are using them as a way of controlling their people. So,
Yeah.
again, most people in China don't worry about that. They have a credit account that covers everything that they do that involves money transactions. And the Chinese have keep up their credit rating, but if you do something that angers the government, it will reduce your credit rating. So this is one way that they keep everybody in line. So it's a two-edged sword. That we really wish there were more Estonians and fewer Chinese.
Yeah. Now, you come from years of experience with engineering, mathematics, and system development. For quite some time now, this agile movement has been very active in promoting agile techniques.
Mm-hmm.
So, do you have some reflection on what is good about the agile techniques and movement, and what are they missing? What is going wrong? So,
well, I think some people feel that the earliest approaches to agile were exactly what everybody should do. So, back with extreme programming, you want to be extreme about everything, and there are times where you can get in trouble if you're trying to be too extreme about something. With Scrum, it's basically saying that you're going to do things within 2-week sprints, and so you should start with doing some of the easy things that will give you some experience with what your users really want. But again, easiest first is not a good example, and particularly for qualities. Basically, the user can say, as a user, I want the system to be secure. And Scrum will say, okay, security is a story. So, well, let's see, what are we going to do in sprint one? Well, we don't have anything to secure, so we better build some stuff and then try to secure it.
Right.
But if you do the easier things first and without thinking about whether they're going to be securable, then you're going to get an unsecurable system.
You can't build that in afterwards. Security, like after.
Yeah, right.
Yeah, that's so. I think there are some typical system attributes like security, how easy it is to change and update the system,
right.
how maintainable it is,
Mhm.
etc., etc. That I think we both agree they have to be built in and engineered in from the beginning.
Yeah.
You can't. It's not something you patch on in a sprint later.
Yeah, right. Yeah.
Yeah. Now, in your spiral model, how is a spiral different than a sprint? I'm using sprints because very many people are familiar with sprints. But you and Tom with his Evo cycles and you with your spiral models, you have been thinking about this, doing things in cycles for a long time. Do you see any similarities at all, or any?
So fundamentally, what the spiral model is trying to do is to incrementally invest in understanding what your system is supposed to be doing for its users, rather than just doing a bunch of design, it encourages you to do prototypes and demos and the like, to buy information about what's going to be the right system for the users, and so that's an extra expenditure, but it frequently guides the project closer to what the user really wants or needs, and doesn't avoids what they don't want.
Right. So, as I see that, what Tom and I think of as an Evo cycle, but it's a learning cycle. That's what you're explaining.
Yeah.
Right? So it's like you have to learn your way towards what the users and stakeholders are interested in. Okay, and the Kokomo model, if I remember right, is focused on, among others, on lots of these attributes like maintainability, reliability, security. Is this correct, or am I?
Well,
why don't you, rather than me guessing that my way there, why don't you quickly say a few words about the Kokomo, the strengths? What are the core strengths of the Kokomo model?
okay, well, I'll give you some core strengths and then say what are some of the stress points right now.
Right.
One of the soft spots in Kokomo is that it asks you for how many lines of code are you going to build. And most projects at the beginning really don't know. Here again, you can use Kokomo to do sensitivity analyses and say, well, if this thing were to take twice as much code, what contingencies should we put in to make sure that we can accommodate that? You can use the size parameter in lines of code as a sensitivity analysis kind of thing, but again, if you're writing a contract and basing it on some particular Kokomo run, yeah, if you're off on the number of lines of code, you're going to be off on the cost.
This is one of the main things Kokomo model is trying to do, is to understand the cost of.
Yeah, and again, and so people have come up with different alternatives to lines of code. You know, basically, there's function points and cosmic function points and story points and the like. And so, for certain kinds of projects, this is a good thing to do. So, again, had some interesting interactions with Michael Cohen, who's basically did the decks of cards that you basically put down when you're asked, how many story points is this going to take, and everybody turns their cards over, and if everybody says 5, then you take 5 as the way to go. A couple of people say 5, and other people say 13, and other people say 3. But you want to have a discussion, and so it's a way of investing in finding out, why do certain people think it's going to be bigger or smaller or more complex and the like. And so it's a good way to stimulate getting something that explores any uncertainties about what's getting built. And again, if people say 5, and converges on 5, there's sort of a commitment that they've made that says, I might have to spend a few more hours doing this.
Now, you must have worked with many people throughout your career. Who was the most interesting to work with, that really stimulated you or challenged you, or just you found interesting to work with?
Yeah, well, there have been a whole bunch of those, and in the pure software arena, one of the role models was Fred Brooks, who wrote the Mythical Man Month and ran the 360 project for IBM
And you worked together on a project, or was it more like that?
It was more that we were on committees together.
Yeah, okay, so you were
he did a National Academy study on software engineering, and then how can the Defense Department do better at what it's doing. And so, he had a whole bunch of wisdom about, they really need to do more prototyping to understand what their system needed to be doing, and they needed to be more thorough about choosing suppliers that the criteria that said we are going to choose the technically acceptable but minimum cost supplier, and usually the minimal cost did was one of the conspiracy optimism problems, and led to a lot of overruns and that sort of thing. So again, all of those kind of things were things that, as I was trying to look at the spiral model in a way, incrementally understanding the system that you're trying to build and trying to evolve in, and doing prototypes, or we did a couple of studies on additive prototyping. How can the Defense Department do a system that to a very simple prototype and have four bidders that look like the best candidates do their example of it, and you take the best three and say, okay, let's see your more complete prototype, and then you take the best two and say, here's another bunch of money to come up with the framework and the infrastructure for what we'll eventually build. And this was something that was not the usual way that the Defense Department worked, but they tried it a few times and found that it was really a good way to do things.
Right. Now, it's interesting. The prototype, and I like the idea of not just making a prototype, but when you have a competitive aspect in there, they need to step up their game. And you pay them for the prototype even if they didn't win. Yeah. So it was not a loss for them financially completely if they didn't win. They had some finances.
There were problems so basically, if you had the first four submit their prototypes, it's going to take a few months to evaluate those, and who's going to pay for the teams that built the prototypes and are supposed to be ready to take on the next?
They were just sitting around waiting for.
Yeah, and they need a job number to charge their time to. So should the government pay for that, and again, this was something that big companies could outcompete smaller companies because they had a bigger independent research development fund and the like, and they could keep the teams going. The more creative ones didn't have that much money to keep them going while the evaluation was going on and that sort of thing. So there were a bunch of second order complications like that were interesting to try to come up with reasonable solutions for, but no perfect solution.
Now, if you were a teenager again, and you wanted to get into this industry of engineering, maybe software engineering, maybe other engineering, what path would you take? I'm sort of thinking as a recommendation for maybe somebody young looking at taking path choices.
Well, that was again something that I had a bunch of early opportunities to see possibilities. I was, as Tom did, go to Santa Monica High school, and one of the things that they typically had was industry days. And one company that's in Santa Monica is the Rand Corporation, and they were doing all sorts of fascinating computing things at the time. And so after 2 years in San Diego working for General Dynamics, I wanted to get a PhD, but there was no University of California at San Diego at the time. So I went up to LA and then applied for jobs at Rand and Rainbow Woolridge in system development. And basically, with my exposure to Rand, I really wanted to go work for them. And so this was great because they had a huge number of really smart people that you could learn from.
So if somebody is young today, so what I'm hearing is maybe try to get into an environment where there are lots of smart people around you. Is that?
Yeah. And there was similar things when I was in San Diego. I again had this big science fiction and interplanetary travel kind of thing, and so I joined the American Institute of Aeronautics and Astronautics, and typically most of the people that were in the society in the San Diego chapter were older and the like. So when they would have a conference in San Diego, basically the younger members would get the job of picking up the keynote speakers at the airport and driving them to the conference hotel and the like. And so I drove or walked around to a meeting or talked directly or some of these German super rocket scientists and the like. So there was a lot of opportunity to connect with role models
Yeah. So when you were driving them, did you say, "Hey, what? I'm interested in this. Do you have any?" Or were you more shy? Or
well, I would ask them questions about. I've been reading all of these science fiction things about people going to Mars. What do we really need to do to go to Mars? And so those people had been studying that stuff for quite a long time and said, we need to approach it incrementally because it's going to take quite a few months to get from Earth to Mars, and we don't know how long people could go weightless and stay healthy and the like. And so there's a whole bunch of prerequisites that we need to solve before we can just boost the rocket up and have the first guy go to Mars.
Talking about going to Mars,
Elon
Musk, are you following his ventures with SpaceX?
One of my PhD students for grads, Ricardo Valeri, was interning at SpaceX, and he kept me up to date on what they've been doing.
How do they? So I mean, for me that's fascinating. SpaceX, Tesla, how Elon Musk's continue to succeed. Some people might say he delivered late or whatever, but he's succeeding in pushing and creating these amazing rockets, cars. Do you have any insights to how do they succeed in project management?
Again, they need to have super brains.
Yeah.
But they also need to produce. And the like, so he's not a perfect example of what he'd like, you know.
I think I find his work fascinating.
Yeah, right.
Personally.
Yeah.
I really like to follow and see his progress.
Uh-huh.
Success or failure, I find absolutely fascinating.
Yeah, some of the things he's having a hard sell from, probably with reason, but yeah, he has this other company called the Boring Company.
Yeah.
that drills big, deep tunnels, and the California bullet train is now 3 times over budget. It was to be done for $30 billion, and it's up close to $100 billion.
Is this one of his projects? The bullet train?
This was going to be a typical Japanese-style bullet train.
Right. Not his project.
Right.
It's not Elon Musk.
So he was proposing a tunnel
Right.
as an alternative to, because the biggest source of overruns has really been legal challenges of you're taking away half my farm to put your bullet train on, and you don't have a right to do that. So with tunnel, nobody owns the stuff underneath the ground.
Are you sure?
I'm not sure.
I mean, there's just space, right? I know the space, but what
right.
about below?
Yeah, right.
Yeah, it will solve lots of those land issues for sure.
Yeah. And and they get really, again, an unfortunate easiest first approach that they've spent $30 billion actually developing the easiest segment, which is basically going through the Central Valley. And but again, they overran their budget because of all these farm lawsuits and the like. But the really hard parts of it are going to be getting the trains to go through the mountains.
Right.
To get to Los Angeles, you've got to go through a whole bunch of mountains, and to get from the Central Valley to San Francisco, you got to go through another bunch of mountains. Digging underneath
Still have to go.
yeah.
I don't know.
Well, that's what the Boring Company is supposed to solve, but I'm sure there are parts of the mountains that are too rugged or too unstable, and again, you got the San Andreas Fault going across the path of the bullet train.
So I wonder, lots of young people are trying to be visionary, explaining the future. But as long as you have. So with all that experience, being through, going through this whole computer age from the very beginning, and being, right in the middle of it, and a leading force in this. What do you see in the future, 50 years from now, 100 years from now? Where are we going with engineering and with technology and with life?
Well, it's sort of hard to predict because there are a bunch of things that people are going to be doing, but they may have really nasty side effects. There was this Zika virus that was being propagated by mosquitoes. And somebody came up with a gene manipulator that basically
Hold on 1 second. Pavel? Pavel? Guys, can you be a little quiet and help keep the guys quiet in the door there? Thank you. Yes, go ahead.
They came up with something that would make these mosquitoes infertile.
Yeah.
So this solved that problem. If that kind of technology got in the wrong hands, we could make the human race infertile. Where did we go?
Right.
Yeah.
Yeah. So step carefully.
Yeah, right.
Yeah. It's moving fast.
Yeah.
Many possibilities.
Yeah.
But your advice is step carefully.
Be careful. Right.
Yes, Professor Verbe,
Uh-huh.
thank you very much.
Thank you.
It's an honor,
Yeah.
and really appreciate all your contributions to software engineering and the engineering community as a whole. It's fantastic. So, and you're still at it. You are
No.
still years to go. So keep at
Yeah,
it.
we do it, yeah,
And
right.
yeah,
Well,
fantastic.
Tom is the same, yeah.
yeah, you and Tom.
Yeah, we feel that we're extremely lucky to have been born when we were. That we were born in the 1800s. I don't know what it would have been like if we were born in 2015.
With an iPhone.
Yeah, right,
Now,
yeah.
but you said you went to the same high school.
Yeah.
Tom and you.
Yeah.
I don't actually know. Did you know each other, or did you just?
He was a couple of years behind. Yeah.
He was a couple of years behind. So, but you just.
Well, I graduated in 1953, and I think he was 58.
Yeah.
Yeah. But we rediscovered each other in the 60s, yeah.
Yeah. Fantastic.
Yeah.
Thank you very much.
Sure, great.
Really
Yeah.
appreciate it. Thank you.